Good morning. Happy Friday. Welcome to class again. It's going to be a fairly short one today, although, of course, I'm always happy to answer your questions. Today, we're going to be looking at the structure of atoms. So hopefully you've had a chance to work through this a little bit on your own. If not, I would recommend, if you're here now and you want to ask some questions and follow along, great. But I would recommend putting the video away and then actually trying and going through and trying to work this out on your own so that you can try to figure this stuff out. On Monday, for the Monday night class, I'll be going through all of the answers to these things. So you'll still have some time this weekend to work through it. And then, of course, we'll have the quiz next week. All right, so hopefully everything else is going well with your at-home experiments and your article reports and such. All right, let's get started. Okay, so you see behind me here the atoms worksheet, and we're just going to go through. I introduced this a little bit, I know, on Monday night, but I want to talk a little bit more about this because it really is kind of the building blocks for everything else, because we're talking about atoms, right? The smallest irreducible piece of matter. Okay, so in this diagram, as with the other worksheet, as I explained on Monday, there's no real context here. It just gives you this picture and says, here's what this stuff is. And from that, you have to kind of figure out what you need to do. So just take a look at it here. We've got 3 different types of dots: fully filled in dots, half filled dots, and empty dots, standing for protons plus, neutron, no charge, and electron minus. So there's a lot of information right there already. Then they're kind of split into these diagrams. So let's look at this first one, hydrogen. So all 3 of these are named hydrogen, and then this last one is named hydrogen ion. And the other differences that we see are in these little numbers next to the H symbol on the left, the upper left of the H symbol there, and these AMU numbers down here, which again, we don't really know what that's supposed to mean yet. But if we're taking a look at these, we can say, okay, a few things that we can notice, right? We can notice some similarities and differences. And in general, this has nothing to do with chemistry, but just like when you're trying to find something out, get information from a figure, let's say, always look for similarities and differences. That's a nice, easy place to start. So right now I can see that we talked about, these are all have an H. They're all named hydrogen. This one's called hydrogen ion. So what's different about that one? Well, it seems to have this plus here. So that'll become important. Then we can see the these AMUs, and they seem to go up with more dots. Kind of makes sense. We can see that each of them has 1 filled dot. These 3 all have 1 open dot. This one has no open dots. And then we've got no half-filled dots on the left, 1 half-filled dot here, 2 half-filled dots here. So that tells us some information about what's going on and similarities there. And we'll probably look at these other ones here. So let's jump down to the first question. And it says, look at the schematic diagrams for carbon. What do all 3 carbon atoms and ions have in common? So we're looking at this, and what do they have in common? Well, they have different AMU numbers, so it's not that. They're all C's, right? So we might write that. They're all called C. What else can we see here? So let's start looking at these different particles, because clearly having different numbers of particles has something to do with that here. So I've got the 3 different types of particles, right? The filled ones, the half, and the empty. So protons, neutrons, electrons. And let's look at the numbers. So each carbon atom seems to have 6 protons, 677 neutrons, and then electrons is not shown, but let's count them up. So 1, 2, 3, 4, 5, 6. 6 electrons, 1, 2, 3, 4, 5, 6. I see 6 there as well. And then 1, 2, 3, 4, 5, 6, 7 over here. All right. So that's not the same all the way across. So there's some variation there. Um, okay, so let's take a look then. I think we've got our answer. They all have C symbols, and they all have 6 protons. So then let's do the same exercise there with the hydrogen and the magnesium. So we go back up to the hydrogen. We kind of already did this. That one's even easier to see, really. We've got proton, 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 proton. So 1 proton. So you start to see a pattern here, I think, right? And let's see if our pattern that they all have the same number of protons holds for magnesium. So for magnesium down here, we can see that it's got 12 protons, 12 protons, 12 protons, 12 protons. So that seems to fit also, and they have different numbers of the other particles. So for the hydrogen, we can say they all have 1 proton. And the magnesium all have 12 protons. All right, look at a periodic table. Considering your answers to these questions 1 through 3, what is the significance of the atomic number above each element in the table? All right, so let's pull up our periodic table here. I have to make it a little smaller here. All right, so looking at the periodic table back here, let's look at those three elements. So we've got carbon right above my head, and its atomic number is 6. You see the 6 in the upper left-hand corner there. Then we've got hydrogen way over on the upper left there, and that one has 1. And then the atomic number is 1. And then magnesium is Mg. That one's also over there, and kind of like down and a little bit to the right of hydrogen. And that one's atomic number is 12. So I think we've got our answer here. If our atomic numbers are 6, 1, and 12, and we've got 6, 1, and 12 for the similarities, then I think that the atomic number we can find that that is number of protons. All right. And maybe you knew that. Great. Maybe you didn't. That's fine too. Maybe you had it a little bit mixed up and you thought that number had something to do with weight or something like that, because it's easy to get those things turned around in our heads. So that's why I said it's best if you can kind of just put away all of your previous knowledge about this stuff when you start these types of activities and see if you can figure it out just based on what the activity is talking about. All right. So then number 5, now we can start using this rule and start thinking about what's going on. So it says how many protons are in all chlorine atoms. Now chlorine atoms aren't in the figure above, but we can find it on the periodic table. So let's pull that up. And we can see chlorine right over here. And it says, so what's the atomic number of chlorine? Well, it looks like 17. So that is going to tell us that chlorine has 17 protons, right? So 17 protons. Do you think chlorine atoms exist with 18 protons? Well, what do you think? Think about it for a second. What would happen if a chlorine atom had 18 protons? And maybe it would be helpful to pull that periodic table up again. All right, so hopefully you came up with the idea that that is not possible, because if chlorine had 18 protons, then its atomic number would be 18. Remember, we said that atomic number equals number of protons, and what do we see over there? Well, it looks like 18 is argon, Ar, not chlorine. So if we had a particle with 18 protons, that's no longer chlorine, that's now argon. All right. So we've learned something really important there. we've discovered it ourselves here, that the identity of an atom, what an atom is, the name that we give it, is really just a reflection of the number of protons. That's really the true thing that identifies what an atom is. And all these words we use, like hydrogen, carbon, magnesium, and these symbols from the periodic table, are just kind of other ways of describing that. We could have named all the elements 1, 2, 3, 4, 5, 6, 7, 8, except that they were discovered before we actually knew about subatomic particles, so their names kind of were carried over from that, and that's why that is that way. All right, so you can kind of get the sense of how this type of an activity is meant to flow. You look at the models, you kind of figure something out, and then you come up with a broader general rule that really explains what's going on here. All right, so let's look down at the next one here. What is the significance of the superscripted plus or minus symbols to the right of the symbols for hydrogen and carbon? So let's go back up and find those plus and minus symbols on hydrogen and carbon. All right, so here's a plus and minus symbol for hydrogen and carbon. That's the plus on hydrogen, and then there's a minus on carbon right there. So what's the significance of those? Well, a couple things. One, it seems to change the name from just the atom itself, hydrogen, to hydrogen ion, and carbon to carbon ion. So that must mean something. And then we can also look at the other difference there. So again, similarities and differences. If all of these are called hydrogen and this one's called hydrogen ion, then we can say, well, what do all of these have in common that this one is different? And similarly, what do these two have in common where this one is different? Okay, and we can think about that for a second, and we can recognize that the hydrogen has no electrons. You don't see any electrons going around here. The ion has no electrons, whereas the other hydrogen atoms all have one electron. And similar in the carbon, carbon has 6 electrons, and then this one has 7. So that's definitely the difference. Now, what is important about that difference? Or why does that difference suddenly give us ion instead of regular? So let's go down and see. So it must be something to do with charge, right? Because as we're looking at pluses and minuses, and we also got this key up here that tells us protons are positive, neutrons are no charge, and electrons are negative. So that's kind of our clue here, that somehow we're changing the charge of this overall particle. The carbon ion has 7 electrons, which are negative. The others have 6. So what is that doing? Well, in this case, we're looking at the comparison between the count of the electrons and the protons. So if we have 6 electrons and 6 protons, we can expect to balance those charges out. So 6 plus, 6 minus is an overall neutral charge. With the ion, we don't have that. With the ion, we've got, like in the hydrogen, for example, 1 plus from the proton and no minuses because there's no electrons. So the overall charge will be plus 1. In the carbon ion, we have 6 plus from the 6 protons and then minus 7 for the 7 electrons. So we have 1 more electron than protons, and that's causing the imbalance there. All right, so we can write that down there. And then when you get into number 7, now we're starting to talk about the other particles, the other difference, this box, the mass number, which is the superscript on the left side of the element symbol. So now we're talking about, let's get a color here. So now we're talking about these symbols up here. Why does this change from 1 to 2 to 3 and back to 1? Why does this change from 12 to 13? And 24, 25, 26, 24 down in magnesium. So what's the significance of that? You'll also notice that those are defined down here as something called isotopes. So these hydrogen 1, 2, and 3 are isotopes. The carbon 12 and 13 are isotopes. And they can also be written this way and this way. We say that we don't call this 1H, 2H, 3H. We call this hydrogen 1, hydrogen 2, and hydrogen 3. So that's why it can also be written this way. And then the nucleus is the protons and the neutrons. So that must be why they're kind of bundled together in the middle here. All right. So you can start working that thing out. One thing to notice here, and it does say this later on, but it's a common error. Notice that these atoms have these mass numbers, and you'll understand how you define those. But one thing that's commonly confused and maybe taught wrong sometimes is people think that because the atomic number is on the periodic table, the mass number is also on the periodic table, and that is wrong. That is false. There is another number on the periodic table. You can see it kind of like under the thing here, under each atom. That is not the mass number. That is called the atomic weight or the average atomic mass. And we'll talk about what that means. It's actually an average of the different isotopes that exist in nature. But no single atom actually has a mass of that number. It's an average of all of the particles. So we can't use these bottom numbers when we're doing this type of an activity, when we're trying to find out about some subatomic particles, like how many neutrons and protons. When we're doing those counts, we're not using that atomic mass. We're using a mass number, which is different, which is always a whole number. So as you work your way through this activity, kind of the overall goal here is to be able to do this. All right? So without using anything else but a periodic table, you should be able to fill in a table like this. And if you do, you're well prepared for the quiz, for this part of the quiz next week. So we'll go through all the numbers on Monday night. But if you can do something like this and you can find all of these numbers, then you should be in good shape. So how do we do that? Well, you have to really understand all of the definitions from earlier in the packet. You have to know what the atomic number means, what the mass number means, and then how the numbers of those three particles lead to those other calculations: the atomic number, the mass number, and then the symbol with the charge. So don't forget the charges when you look at these symbols here. All right. As you're going through this, if you have trouble, of course, let me know. If this is not clear, I can always jump on and do another video, try to explain things further. Definitely join in on Monday when we go through and look at everything together. And yeah, hopefully everything else is going well with you. I've heard from some of you lately. Some of you I haven't. That's okay if everything is going okay, but please always feel like you can reach out to me and contact me if you need anything. So that's it for this morning, and we'll be back. I'll be back on Monday evening to go through the rest of this. Hope your experiments are going well and you're staying warm. It's going to get pretty cold out there these next couple weeks. And I'll see you, Monday night. Bye, everybody.